So you have to log in and log back in.
All right, good afternoon. Welcome to our very, very interesting virtual event on coronavirus with Dr. Richard Kopek. He is our CTC microbiology professor here on the Central Campus, and he is going to be talking today about a lot of information. Before we get started, if someone asks you to go ahead and register for attendance, make sure that when you're done with this presentation that you go to the library website and hit events, and you can go ahead, there's an online registration. Also, you can see other events that we have coming on. But that's enough about me. We are going to get started. Welcome, Dr. Kopek, and take it away.
Well, thank you very much, and it's great to be here, and it's certainly great that everyone else is here watching this video, so I'm very excited about this. I want to give a little talk today about a video I did in the summer, which I tentatively entitled Potential Pre-Exposure Prophylactic Strategies for SARS-CoV-2, and basically, this summer I was thinking about the kinds of things one could do to either protect yourself from this particular virus or to at least attenuate the effects of the virus, that is to say, to ensure that you have an asymptomatic or a very mild disease if you're exposed and infected by this particular virus. Now, pre-exposure prophylaxis in microbiology is a pretty well-developed concept. For example, with HIV, which causes AIDS, there's something called pre-exposure prophylaxis, and it involves taking one pill every day. It's called Truvada. It's composed of tenofovir and M-tri something or other. I kind of forgot the name of that. It's M-tricidabine, and if you take that every day, your chances of contracting HIV sexually is like reduced by 99%. So this is really quite impressive. It's clear that you can reduce the likelihood of contracting various viral diseases by taking certain kinds of compounds and doing certain kinds of things. And so what would be the most likely sort of compounds that you could take to protect yourself against this particular virus, or the kinds of behavioral strategies that you could do to protect yourself from this virus? That was what I was interested in this summer, so I made a little video on it. Now, I say a little video, it's actually an hour and 42 minutes long, and I don't want to show the entire video here tonight because nobody would stay to the end. But I do have some excerpts from it to give you a flavor for give you an idea of what's in the video, and for those of you who are intensely interested in, you can certainly access the video and watch the entire thing. So with this in mind, let's watch the first segment here. The first segment is about the virion ultrastructure, some basic stuff on viruses, the 6-foot rule, which is again a kind of a strategy to protect yourself from being infected by the virus, and then finally some stuff on LD50 and ID50s, which is an important concept. So let's look at our first segment.
Excuse me, I'm going to go ahead and start back on that because somehow we got unmuted. We're good. Just keep going.
Cindy, we haven't been able to hear the video this whole time. I'm trying to get a hold of you.
You can't hear the video?
No, we hear Dr. in the background, just not the video itself.
Okay, Dr. Kopek, if you wouldn't mind hitting mute, and we'll go ahead and go do it again.
The what now?
The mute.
Oh, hit mute?
Yes, if you will hit mute. Did you hear any of it?
No, we didn't hear any of the video. It was so quiet, like it just didn't take control.
And typically, what you have are these protein or glycoprotein spikes, and these are the things that are actually going to last on.
And we can't see it anymore.
For a while, there's just some is an enormously huge molecule surrounded by a protein coat, and then
We still can't really hear it. It's very muffled. You can't make out anything.
acid surrounded by an envelope. Now, what is an envelope? So an envelope is actually part of the cell membrane. So here's my viral capsid, this protein coat called capsid. There are some pieces with one piece or several pieces of nucleic acid. And some viruses, when they get out of the cell, feel a bit of this membrane. So typically what a virus does is it makes a bunch of proteins and sticks the proteins into the membrane, and then it spreads out. It's your membrane, and it's protein sticking out as a spike. This is exactly what COVID-2 does. So COVID-2 is a spike in a membrane. So what's a membrane? I draw a cell, so I draw a cell like that. It has a nucleus, you think it's cells. But what is this line? That line is a phospholipid dimembrane, bilayer, like a bunch of proteins that call a membrane. And so this is a fairly delicate thin bilayer, this is a molecule. It's maybe 10 nanometers.
Cindy, it's not working. I think you have to stop because I don't think the video is going to leave. You can't hear anything you say. It's
Okay, well,
hello's over again.
okay. Well, maybe you can just go ahead and give us a, just tell us about it, Dr. Kovac. Because for some reason the video is not cooperating.
Okay.
So, would you just please just tell us, and I will mute myself and give you the floor.
Okay, well, that's a pleasant surprise. Basically, that particular segment was about some of the viral ultrastructure. Viruses are essentially little pieces of nucleic acid. In the case of SARS-CoV, it's actually one long piece of RNA, ribonucleic acid, and it's encased in a protein shell, and then around it there's an envelope. This is actually a phospholipid bilayer that it steals from the cell, and then it buds out of the cell, and it can infect other cells. The interesting thing about the envelope is that envelope viruses are pretty easy to disinfect. That envelope is only about 10 nanometers in thickness, so there are plenty of disinfectants that'll go after it. So that's one nice thing about this virus in terms of not getting it. The other notion is this 6-foot rule. Now, right now, I'm talking to you, and although you probably don't know it just by looking at my little picture there, and I don't know how big my picture is. I see a little teeny tiny picture in my screen. But the thing is, I'm emitting all kinds of particles from my mouth, and they're of various sizes. They range anywhere from maybe 100 micrometers in diameter or even bigger. In other words, you could see these things. And if you ever talk to someone who's kind of juicy, if you know what I mean, you can actually feel the spittle, if that's what the word is, on you when that happens occasionally. But everyone will emit particles, and some of those particles are really tiny, like less than 5 micrometers in diameter. If they're less than 5 micrometers in diameter, the effect of gravity on them is largely negligible, and they can remain in the air for hours, maybe 3-4 hours, and they can travel great distances. They could go if they get caught on a current of air, they could go for many meters. For larger particles, we're thinking that the virus exists in larger titers. That is to say, there's more virus in a large particle than a small one. So you're more likely to get infected by the virus if someone is close to you, because the reach of those large particles, greater than 5 micrometers, is about 6 feet. And so they fall out of the air pretty quickly. They're subject to gravity, and therefore this leads us to the 6-foot rule and the idea that you should wear a mask, because the big particles were thought to basically transmit most of the virus, and so you want to stay away from those. And that does make sense. Now, other countries like Sweden and so on actually don't require masks, and their infection rate, hospital case rate, and so on is reasonably low. I mean, compared to France or England, at least it is. So, it's really not clear what the effect of that is. The other thing is those small particles may transmit the virus. You just don't know. There's certainly evidence that that's the case. Now, this is important because there's something called LD50 and ID50. And let me talk about LD50 because that's an important concept. The LD50 is a lethal dose in which 50% of your test animals will develop an infection and die from it. In other words, as you increase your infectious dose, as you challenge test animals with more and more virus, of course, more and more it will come down with it, but more and more will die from it. The severity of the disease is a direct function of the amount of infectious dose you're giving these animals. It's all animal studies, of course. And so the thing is, you want to avoid big doses of it, because in the news there's news accounts of doctors who treat patients, and they're relatively young and they get it and die, and presumably because that's their infectious dose is so high. Now, associated with that idea is this notion that you can actually vaccinate yourself, a kind of vaccination, with low doses of the pathogen. There used to be something in microbiology called variolation. Now, variolation is an old concept that dates from the time of smallpox. Smallpox doesn't exist anymore. Smallpox was a brute of a disease. It was highly transmissible, highly contagious. People got it. You got horrible poxy pustules all over your body, and about a third of all people died. So very, very bad. It was eliminated due to public health measures and vaccines. But in the old days, before generous vaccine, what they did was they would take teeny tiny amounts from pustules and intentionally inoculate people who didn't have the disease, but with a very tiny amount. And the notion was that they would get a mild form of smallpox and therefore be immune. So if you can limit your exposure to this particular pathogen, then the idea is that you'll get a much milder, you'll be asymptomatic, or the disease will be very mild, and you might even be able to immunize yourself in that way. So this notion of a 6-foot rule, don't get a big dose, don't be around people who are sick and coughing, is a reasonable notion. And I think it's a reasonable prophylactic strategy, social distancing and the mask. However, I'm not like it's clear that people still get it, right? Whether you do that or not. So what I was thinking about in the summer, are there any kind of drugs that I can take that would protect me from it? Like Truvada can protect you against getting HIV infections. And more to the point, are there any over-the-counter medications? Because you can't go to a doctor and say, "Oh, give me all this stuff because I think it's a good idea." You're not going to get a prescription for that. So are there over-the-counter things that you can do? And I went to the research, and if we could only show my little video there, I could show you some of the scientific papers that these notions are based upon. But there are compounds that you can go out and buy on Amazon or eBay or at Walmart, and they do have antiviral properties, and they just may protect you from developing this virus, of getting the disease and ultimately dying from it. So I wanted to identify, some of those compounds, and maybe even take them myself, because I'm not crazy about getting this disease, especially at my age. So the compounds I became interested in up front were two compounds. One of them is zinc. Now, zinc is a mineral. You can go out to Walmart and buy zinc. It's you get it naturally from foods and so on. There's a lot in certain seafoods. Oysters, I think, have a lot of zinc. But the thing is, if you look at the virus's life cycle and cellular cycle, here's the thing about the virus. It's an RNA virus, and it replicates in our cells, but it uses a special enzyme to make copies of its RNA genome, or its RNA genes. And that enzyme is called RNA-dependent RNA polymerase. Now, RNA-dependent RNA polymerase is something we as humans do not have. We don't have that. So the virus actually has a little gene, and it makes protein, and the protein is the RNA-dependent RNA polymerase, so it can make copies of itself. Well, it turns out that zinc can actually inhibit that process. This enzyme is sensitive to relatively high concentrations of zinc, and if you can get enough zinc into your cells, then you'll inhibit the replication of the virus, give your immune system more time to fight it, and so on. So, plus zinc historically has all kinds of antiviral properties. That's been known. If you look at the literature, there's lots of literature, lots of proposed mechanisms how that happens. So that was pretty clear. There's a problem here, though. And the problem is, how do you get a lot of zinc in your cells? Because there's something called homeostasis in biology. This is a very fancy word, and what homeostasis means is that cells and your body in general try to maintain a certain range of values, a certain concentration of various ions and substances in your blood, in your cells, and so on. And there are feedback mechanisms that ensure that that's the case. If the levels get too high, there are mechanisms that kick in that lower it. If it gets too low, there are mechanisms that kick in that increase it. And all kinds of mechanisms that do that. So our pH in our blood is pretty constant, that kind of thing. What about zinc? Well, yeah, I mean, you can only get so much zinc. If you're deficient in zinc and take it, of course, your zinc levels will go up. But there are compounds that are called zinc ionophores. And zinc ionophores are actually capable of getting extra zinc into your cells so that your zinc levels are increased from what they would normally be. Now, there's an interesting drug that can do that, and that's hydroxychloroquine that our President Trump used to take, and the New York Times didn't like that. But the thing is, there are a number of these compounds. And of course, hydroxychloroquine, which is an anti-malarial drug, that's a prescription drug. You can't take it. It has some unpleasant side effects. But there is something that you can get over the counter that is a zinc ionophore that has been shown to increase your zinc levels, and that's quercetin. That's quercetin. So if you're watching my video in the future, if you're ever going to do that, and after but if you're ever going to do that, quercetin. It's Quercitin, and it's cheap. It's what's called a phenolic compound. It's a bioflavonoid. It's found typically in foods. What kind of foods? Cauliflower, broccoli. It's found in red onions. It's found in blueberries. You get all kinds. You get probably milligram quantities of this every day, and a little bit more if you eat like your mother told you to eat. Your vegetables and fruits and all that kind of stuff. So if you take them together, you can force a little bit more zinc into your cells, and that should slow the viral replication down. So those are two good candidates for pre-exposure prophylactic compounds that you can go out and buy today. Now, let me just emphasize, I'm not a medical doctor. I don't suggest anyone do this. I don't give medical advice. I'm an incompetent fool when it comes to medicine. So please don't take this as some recommendation or something that you should do. If you're going to take zinc supplements, well, you can go out and buy them. They're not that dangerous, but huge amounts of zinc are not good for you. They have unpleasant side effects. There's an upper tolerable limit for zinc. I think it's like maybe 40, 45 micrograms a day. I think it's micrograms. I'd have to check. But in any event, well, maybe it's milligrams. I forgot. I'm doing this a cappella. I'm doing this offhand, and you guys can't expect world-class stuff.
Well, we put the link in the comments, Dr. Kopak, so they will be able to see your videos, just not right now while you're talking. So
Okay, well, that's reassuring that they can do that. So anyway, a little bit is good, a lot is not good. 2 aspirin will cure your headache. 1,000 aspirins will kill you. So please don't think more is better. People always do that, but it's important not to do that. Anyway, if any of you are tempted to take zinc or quercetin or any of this stuff, please see your medical doctor before you attempt that. That's my advice. But I'm talking about me and my research, not research, but readings, I guess, over the summer. So, please note that. Okay, so zinc and quercetin are good candidates, right? They are. Are there any other candidates? So I was thinking about quercetin, and quercetin is a bioflavonoid, it's a polyphenolic. What about other polyphenolics? There's a real famous one that leapt to mind, and that's resveratrol. Now, resveratrol, you may have heard of it. It supposedly has anti-aging properties. Resveratrol is thought to delay the onset of various degenerative diseases. At least that's true in mice. So if we were mice, it would be the thing to take. It's commercially available. It's cheap, and it occurs naturally. As a matter of fact, you can, if you drink wine, I think there's about 0.27 micrograms of that in wine, and red wine at least. Good red wine. So I'll go home tonight and have a nice glass of red wine after this to relax. But it is a nice compound, and it can't be that toxic because I drink a lot of red wine, and here I am. So anyway, resveratrol. So if I looked in the literature, and that has all kinds of antiviral properties. It has antiviral properties and has been shown to inhibit things like Epstein-Barr virus, enterovirus, herpes simplex virus, the influenza virus, respiratory syncytial virus. It does. And there's a recent preprint article that's available now where they study the effect of resveratrol on SARS-CoV-2. And yeah, it does have activity against it. So it's a compound that's also a prime candidate for pre-exposure prophylaxis, as I call it. Okay, so those are really, really interesting compounds. Are there any other compounds? Well, there's a couple, and I'll immediately mention vitamin C. But why vitamin C? Well, vitamin C has all kinds of immune functions. That's clear. If you don't get enough vitamin C, you get scurvy, for goodness sake. And scurvy means your teeth fall out, you get easy bruising, and you get all kinds of infections because your immune system collapses. But the thing is, the big amounts count. I mean, we know that if you have enough vitamin C, that doesn't happen. Do large amounts help you? There's evidence that goes both ways. The thing about vitamin C, though, is that it helps you absorb quercetin, because quercetin normally in foods is connected to a little glucose little glucose molecule. It's glycosylated, and that helps you absorb it. Without that, these polyphenolic compounds are very difficult to absorb. So if you take vitamin C, that supposedly helps you absorb it. And so I do take vitamin C because of that. And there is evidence that they work synergistically too, by the way, because vitamin C can reduce, I guess, quercetin. It can regenerate it, because quercetin is also an antioxidant, which I'm not going to go into. I'm not, because this is off the top of my head here. By the way, I need a little preparation for that. But anyway, okay. How does this thing kill you? How does SARS-CoV-2 kill you? Well, there's a couple of killing mechanisms that are worth mentioning. The premier one is a cytokine storm. So what's a cytokine storm? Well, suppose you touch something really hot and get burned, your finger gets burned. What happens to it? Well, it blisters up and you get all that fluid in a blister, right? And it's hot and it's painful and throbs. That's an inflammation effect. And it's due to the release of certain chemicals and the activation of certain chemicals that are the result of the injury. And this leakiness of your blood vessels and dilation of your blood vessels, this is a good thing, because it allows white blood cells to reach the source of the injury, and your white blood cells can eat all of the bad guys there, eat the dead cells, and if there's an infection, you also get inflammation and so on. So it's a good thing, but it's not a good thing when it goes nuts. And this disease can lead to the inflammation of your entire lungs. And so you have to imagine your entire lungs filling with fluid, just like that blister fills with fluid. And proteins leak into the fluid, it turns into a kind of gel, and you can't get gas exchange in the alveoli of the lungs, and you essentially die from lack of oxygen. In fact, one of the strategies when that happens with SARS-CoV-2 is to shunt your blood to an artificial heart-lung machine, oxygenate it artificially, and put it back. Except it usually doesn't work, and the guy ends up dead anyway. Okay, so this cytokine storm is the result of an immune dysregulation of the inflammatory response. There are all kinds of complicated mechanisms that your immune system has to get inflammation, but not too much inflammation, because too much inflammation can kill you. And the virus seems to screw up that regulation. And is there anything that can help with the regulation of your immune response in terms of the cytokine storm? And there's one, and it's dramatic, and it's vitamin D. And vitamin D is your immune cells have vitamin D receptors. They require vitamin D to function properly. If you're low in vitamin D, your immune system is not functioning properly. And so consequently, vitamin D seems to have a real effect in attenuating that storm. Now, there's a paper out this month, and I wish I could show it to you here, but our video is not working, as you may have heard. There's a paper out. It's from Spain, and what they're doing is they're giving vitamin D to hospitalized patients. Okay, and they're giving it in the form of calcifediol, which is activated vitamin D. It's what your liver does to the vitamin D that you take. So if you ever read the paper, you'll see calcifediol, not vitamin D. But it's the same thing. It is. So they separated at random into groups who were hospitalized. 50 got the vitamin D, and 26 didn't get the vitamin D. They were treated with hydroxychloroquine and azithromycin, which is standard treatment. But 50 got vitamin D, 26 did not. Of the 50 who got the vitamin D, 50 got vitamin D. One of them had to go to the intensive care unit, and nobody died. They were all discharged with no complications. Of the 26 people who did not get vitamin D, 13 had to go to the ICU, and two died. Two of them died. So this is an enormous difference by virtue of just giving someone vitamin D, and vitamin D has been shown to prevent flu and attenuate flu. It has a real immunological consequence. So vitamin D is a prime candidate. A lot of old people have very low levels of vitamin D, and I do take vitamin D. If you take lots of vitamin D, that's toxic. It's a poison at high concentrations, so you don't want to take a lot of vitamin D. More is not better, but 25 micrograms a day is the dose for vitamin D. It's sometimes referred to as 10,000 internet. I think it's 1,000 international units. So you should do that. Well, I shouldn't say that. I don't recommend that anyone do anything. I'm not a doctor, but I do it, and I think it's a good idea. It has a real effect. That's a good thing, in my opinion, good candidate for pre-exposure prophylaxis, as I call it. Okay, so vitamin D and vitamin C. What else can we say about that? Pepcid. Let's talk a little bit about Pepcid. Pepcid is an antacid. It is. And the active component of Pepcid is a compound called famotidine, and famotidine is a proton pump inhibitor. It inhibits histamine release and so on. They focused on it by doing a bunch of what they call in silico research. I'll do that air quotes here. In silico research, which is to say they looked at the sequence of the spikes on the virus, and they tried to match it with a bunch of compounds in a computer, and they found some homologies there that predicted the famotidine would bind to it or interfere with it. Also, some of the proteins that it made, the proteases especially. And so people started to look at it very carefully, especially after they noted that people who were on it had a much lower hospitalization rate. Well, they had a much lower complication rate, and they didn't die as often as people who were on these other antacids. And so it became an interesting compound, and there are studies about that. And statistically, it seems to have a real effect, that if you give people famotidine, it does reduce complication rates. Now, the thinking is today it has nothing to do with the virus, as a matter of fact. They say that's been more or less disproven. What they do say is that famotidine is a histamine H2 receptor blocker. I mean, it does that. There's no question that it does that. It's designed to do that. It blocks histamine, but it blocks histamine H2 receptors on mast cells. And by mast, I mean M-A-S-T. Now, mast cells are located throughout your body. They sort of permeate tissue. And what they do is release histamine. And what does histamine do? Well, it causes inflammation. And this is part of the killing mechanism that SARS-CoV-2 has. This dysregulation of the immune control of inflammation, and then too much inflammation in the lungs, you die. So if you can reduce inflammation with something like famotidine, then maybe that's the mechanism. And people are sort of keying on that mechanism now instead of the other ones. It's possible that that's something you could do if you ever get sick. And I would certainly consider it if I was actively ill with it. I wouldn't take it as pre-exposure prophylaxis because I want to digest my food, to stop stomach acid. So, there's a downside there. But nonetheless, I would certainly seriously consider that. Okay, let's continue with this. What else? Nicotine. Nicotine. So nicotine is peculiar because they found, especially in France, there's a lot of smokers in France. I think it's like over a quarter of the population smokes for some odd reason. And what they found was that there were very few smokers. There were very, very few smokers actually getting this disease and ending up in the hospital. So the notion was, well, maybe it's smoking. Maybe smoking is protective. But this is counterintuitive, of course, because smoking is always bad for lung infections. But nonetheless, they looked at smoking, and especially they looked at nicotine, which is, of course, a component of the smoke. And nicotine, they looked at so they were looking at nicotine, and one of the things that they noticed when they were looking at the virus spike, because they were trying to figure out what was going on here. So they looked at the viral spike proteins. They looked at that. And they found that there was a bit of the protein on that spike that was very similar to snake venom, specifically like blue crates and Indian crates, which are terrible snakes and very, very lethal. But what does that snake venom do? It actually binds to acetylcholine receptors on nerve cells. That's what it does. And of course, acetylcholine receptors on nerve cells are involved in neural transmission. And in fact, crate venom will paralyze you. You can't breathe and you die. It takes about, I think, a day or something like that. But anyway, what was I saying? Okay. So what does this have to do with nicotine? Well, nicotine binds to acetylcholine too. There's something called nicotinic acetylcholine receptors, and they're called nicotinic acetylcholine receptors because they bind nicotine. And so the thinking is those receptors are protected because when you take nicotine, it binds to the receptor, and this blocks the interaction of the virus with the receptor, because they were predicting that because the receptor has a snake-like bit of protein, it would bind to the acetylcholine receptor. We always think of the virus as binding to the ACE2 receptor, ACE2 converting enzyme receptor, and it does. But it interacts with all kinds of other proteins on the surface of cells, like TMPRSS2, which is a protease which activates the spike. And apparently, it may be interacting with acetylcholine receptors too. Now, that's pretty interesting because you probably read where people with this disease might lose their sense of taste or smell. And this is clearly a neural phenomenon. There are ACE receptors on nerve cells, but there are also acetylcholine receptors. So maybe it's doing that, and maybe nicotine can interfere with that process. So, I certainly haven't taken up smoking, and I don't take nicotine. But, if you actually were losing your sense of smell and taste, would I take nicotine? Well, maybe in the form of nicotine patches, which you can buy like on Amazon or, Walmart sells, CVS sells them. They're usually like, I think they're the equivalent. I think there's like 21 milligram patches and 14 and 7 milligram patches. 21 milligrams is the equivalent of about 10 cigarettes a day. So I don't know how much that is because I don't smoke, but it's a reasonable amount of nicotine. And is that a reasonable thing to do if you're sick? I don't know. I would certainly talk to my doctor about that and ask him, and he'd probably say, "Are you crazy? Don't do that." But nonetheless, if again, it's just one of those compounds that's interesting, not so much as pre-exposure prophylaxis, but as a kind of a treatment option if you have a mild case. And again, I don't recommend this. Not a doctor. Don't know anything about medicine. But it's something I would be talking to my doctor about if I actually did get this disease. And there are other things like that as well. I noticed that President Trump was taking a bunch of stuff. He was taking, I know he's taking zinc, but he was also taking melatonin, which is an antioxidant. In the talk, I talk about all kinds of. I talk about NAC, but I don't want to talk about that here. That's beyond the scope of my impromptu little lecture here on this. But let me talk about one more thing, because I see I burned up a little bit of time here. So people have at least got their money's worth. The one more thing I want to talk about is hydrotherapy. Hydrotherapy. So in the early days of medicine, this is like 1900s and so on, there was something called hydrotherapy. And what hydrotherapy was they would subject you to very hot showers and then very cold showers. In other words, they would you would have to essentially go into a sauna but you were heated up by water, so they called it hydrotherapy. And there were a number of regimens of hydrotherapy. So you might have to have cold and then hot and then cold and then hot, cold, hot showers, that kind of thing. And that supposedly was good for you. That supposedly protected you from disease. That was the thinking back then. Well, no one thought about that, for the last 100 years, I suppose. But during the great pandemic of 1918, when influenza swept through the country and killed millions of people, they recently went back and looked at some of these sanitariums, as they were called back then. Today we think of sanitariums as for crazy people, but back then it was for health reasons. And they found that certain, the Adventists who ran these sanitariums, who did the hydrotherapy, that their death rate from things like the influenza pandemic of 1918, 1919, it was very low. It was like maybe a tenth of what it was out in the general population. And the thinking was, well, maybe that has something to do with hydrotherapy. So, okay. There are some papers in the last 10 or 15 years looking at the effects of hyperthermia on white blood cell count. And there's certainly some evidence that this hyperthermia, increasing your temperature, can increase your white blood cell count. And especially something called natural killer cells and monocytes, which are important in SARS-CoV-2. People with low monocyte levels don't do well. And the thing is, this is reasonable. When you get a fever, you're getting a fever for a reason, and the reason is the high temperature activates all kinds of genes, and these genes basically lead to an enhanced immune response. Clearly, you increase interferon and stuff like that. So it's a reasonable notion, and the idea that alternating temperatures from hot to cold, that sort of dynamizes or enhances or turbocharges that response for whatever reason. So there are these regimens for hydrotherapy. There are. And I'm just trying to think of the time courses offhand. I've done a couple. You have like maybe 30 seconds of a cold shower, say. And by cold, I mean there's no warm water at all. It's right out of the faucet. So you're talking anywhere from between probably about 60 degrees Fahrenheit, 60 to 70, depending upon the time of year. And then 3 minutes of a really hot shower, maybe like up to 110 degrees Fahrenheit. which means you're sweating under the water. It's very, very hot, and then back to cold, and then maybe a minute of that or something, and then back to hot, and so on. Do that 3 times, and you're ready to stop because it's very unpleasant. But nonetheless, some people argue, and there is evidence that this does increase your white blood cell count and activity of the white blood cells, and so that therefore it's a good strategy to do if you want to protect yourself from these from SARS-CoV-2 from the thing. Well, at the end of my talk, I give a little personal note on what I do and how I manage this stuff. But again, it's just something I personally do as the result of my kind of lackadaisical research over the summer. And does it have any effect at all? Does it have any effect at all? Well, you don't know, right? I mean, you just don't know. I haven't died of SARS-CoV-2 yet, so maybe that's a good sign. But it may be very effective. If it may not be very effective at all, who knows? But you look at the evidence. I think it is probably something that does something. So it's something that does something. It does, and it's cheap. It's easy. I consider it to be reasonably safe myself, so I do it for me. People are different. They have different medical conditions, and some things I'm sure with certain medical conditions you would not want to do. So if anyone is interested in doing those things after seeing my video, because this is just my talk, I'm doing offhand, for goodness sake, please don't judge me on this basis. But nonetheless, see a doctor. Talk to your doctor about it, and you might want to consider it. So that was essentially the essence of my talk. I have some other bits and pieces there. It goes on for 1 hour and 42 minutes. I think I've gone on for over half an hour. I think, and I'll stop there. And if anyone has any questions about any of this, I'm happy to answer any questions. And if not, I hope you weren't too disappointed by not seeing the video. And I'll certainly wave goodbye if you're leaving now. But if you're hanging around, and try and answer the question.
Well, we will let you know that we did put your links in the comments, so they can go ahead and see the videos. Lee will let us know if we have any questions. It's just good to know that eating your fruits and vegetables with your vitamin C and all your antioxidants and your blueberries and vitamin D, your sunshine, those things which are good for you, not too much, it sounds like it's really helpful in this. So Lee, were there any questions in the comments?
No, there's not any right now.
Okay. Well, Dr. Kopek, we apologize that our video wouldn't come through loud enough for everyone, but that was an amazing information. We truly believe it, that we've learned so much. If we get any comments in our comment section, we will definitely forward them to you so that you can go ahead and answer the specific comment. We want to thank you, and everyone, make sure that you check out the video on our CTC YouTube and our library YouTube, and maybe Lee can work her magic and put the links together with all of everything. So we will get it together one way or the other. Thank you so much for joining us this afternoon. Check out our events page, because our next event is going to be our Workforce Solutions, October 19th, 20th, and 21st. And we're going to go ahead and have it at 12:15 instead of your normal 12 o'clock. So Thank you, Dr. Kopak. We really, truly appreciate it. You did wonderful as a cappella.
Okay.
Okay?
Just threw you in there and said, okay, wing it. You did great. Thank you, everyone, and you have a good evening.
Okay.
Okay.
Bye-bye. Don't leave us, Dr. Kopak, yet. Don't leave us.